Hello everyone again. My name is Victoria Hodoleanu. I'm a senior data analyst at Accenture. Today I'm going to talk about one of the projects we've been working on. Its subject is predictive maintenance for industrial assets. I'm going to talk a bit about what predictive maintenance is, our business case, some details about the implementation, the model description, some brief results, and if anyone has any questions, I'll be more than happy to answer them. So first of all, predictive maintenance is very widely used in the industry. It aims to identify problems in factories in order to intervene and fix them before they cause failures or delays in production. A similar business case is the one I'm going to present today. The setup. So our environment consists of approximately 10,000 assets. These assets are of various types. They can be motors, pumps, bearings, gearings, and have on them mounted some sensors. These sensors collect data. So we have daily, we receive KPIs, or better said, measurement types. These measurement types can be skin temperature, vibration, running time, bearing condition, and so on. And these are collected every day via gateway or via mobile. What we try to do is for the motors, because we did the prediction separately for each type of asset, we try to predict with 10 days in advance if a motor will reach an alarm state. The alarm state is given by some of the measurement types that come with the data collection. These measurement types also have, besides the measurement value, they also have a health status associated. The health status can be normal, alert, and alarm. The alarm state was what we were interested in. The setting seems pretty simple, easy to understand. The main problem we had was with the nature of the data, because the data doesn't always come when it's generated. Sometimes it comes with delays. We also had motors that were very new, so we didn't have historical data for them, or enough historical data. Regarding the implementation, apart from the operational database, we had a big data database in which we stored the training data. This database was also updated daily with new data that was afterwards sent to the predictive model. This model was constructed in Azure Machine Learning Studio. From the model, we got back some scored data, which was afterwards sent to the backend and saved in the database for us to do afterwards the comparison and see exactly how well our model worked. Regarding the prediction model, we had quite a lot of data. So we had data covering 2019 and until early 2021. These sensor readings had an intraday frequency, which meant that for most of the measurement types and assets, we had 24 readings in a day. This was a little too much for our model. We didn't need that much information. So we did some aggregations on them. Nothing very complicated, so minimum, maximum, means, standard deviations. And we also constructed a series of KPIs which showed us how a motor behaves in terms of alarms. So what percentage of the last 30 days does it stay in alarm state? How many days pass between two consecutive alarms, the minimum, the maximum, and KPIs like that. These two sources were basically used as input for the data analysis and modeling step, which was done in Azure Machine Learning Studio. We decided to go further with two models. The first model was for the assets for the motors for which we couldn't construct the overall alarm behavior KPIs simply because they were pretty new motors and we didn't have enough historical data. And the second models were for those motors which go into alarm state repeatedly. Looking more in depth into the model, the main issue we had to take care in the data cleaning step was how we should handle the periods with gaps. Because if we're missing a day in between those 30 days, we don't know exactly what happened there. That motor could have gone into alarm state and we wouldn't catch it. So we had to make some adjustments. If we didn't disregard all that period, we could simply adjust it to be comparable with the other assets that had indeed 30 days of data. For the feature engineering part, I already said we did some aggregations at the daily level, and we constructed those overall alarm KPIs. The model selection. For the model, we chose, as I said, to build it in Azure Machine Learning Studio. We experimented with various techniques and parameterizations. We tried the support vector machines, decision trees, and random forest. We chose to go forward with the random forest. I'm going to explain in a bit why we did so. And for the validation, obviously we validated the model on data it hadn't seen before. But one thing to mention is that because our data had a time series characteristic, even though we didn't treat it as a time series per se, we did analyze its performance on intervals that weren't included in the estimation. So if the model was constructed on data until January, we tested its performance on data starting with February. Regarding the choice of the model, well, we chose random forest because it was better than the other models that we tried, obviously, but why did it do so? So for the support vector machine implementation in Azure Machine Learning, it was a little bit more rigid than for the random forest and the decision trees. So you didn't have the choice of a kernel. You only had the default option, which was a linear kernel. For us, that didn't really work with the data we had. This could also be seen when we analyzed the results because it had trouble in identifying the motors that went into alarm state. For the decision trees, it's already known that decision trees have a problem when the data is correlated. And even though we mitigated this issue partially by choosing the data that doesn't overlap for an asset, it still had some signs of overfitting. So we did much better on the test set than on the validation set. These problems wasn't reproduced on the random forest. It also handles well missing data. It's also easy to explain, and it's very well, very easily adjusted for retraining. For the results, well, first of all, as probably everyone expected, the data we had to work with was imbalanced. 90% of the motors don't actually reach alarm state. and only 10% of them reach alarm state in a particular day. The accuracy we had was 94%, but given the nature of the data, so the fact that it's imbalanced, we had to look also at precision and recall. Out of the assets, or the motors more specifically, that we said would go into alarm state, we managed to identify 85% correctly. 15% we said would be in alarm state, and they actually weren't in alarm state. And for the recall, the results are a bit more modest because out of the assets that were in alarm state, we identify 53%, with the mention that 40% of these results actually were assets that went into alarm state, but went into alarm state earlier. So started being in alarm earlier. So probably an adjustment to the model could be adding another class of assets that go into alarm state earlier. At the same time, these 40% should be caught by earlier runs of the model, because the model is run every day for all the assets in that day, so it shouldn't be a problem. So this is pretty much it from my side. Thank you. And if anyone has any questions.
Hi, Victoria. Yes, there are a few questions. It's good that we have time for them. So the results were better in regard to what metric?
So the results were better for random forest in terms of precision and recall. So the accuracy didn't change very much, just because we are dealing with 90% of data from one class. But if we look more in depth at the precision and recall for the random forest, it worked better, much better. For example, the SVM, the support vector machine, didn't manage to identify too many motors that went into alarm state. It did good overall because it did at least 90%, but it didn't do well at identifying what it was supposed to do.
Got it. And have you compared against other models such as XGBoost?
We have compared against other models, but not the one mentioned. I'm not sure if it's implemented in Azure in Machine Learning Studio. I know you have the possibility to call libraries from Python. So theoretically, everything that's implemented in Python, you can also use in Azure Machine Learning Studio, but we didn't try the XGBoost one.
All right. There's also why in the prediction distribution the true positive is only 5%.
Because the overall percentage of positives was quite low. So we didn't have that many assets that went into alarm state in one particular day. So that's why it got right. I can check. So out of the positives, it got right 53% basically, out of all the positives.
Mm-hmm. All right, so yeah, there's still some room for improvement.
Of course.
But there always is. And did you use any kind of aggregations for daily data? And if so, what kind?
Yes, so we didn't use anything very complicated. The fact was that we got 24 points for each measurement type in a day, and we wanted to use the maximum, the minimum, the average and the standard deviation. And we also use the lagged values. So we didn't look only at the value that, for example, skin temperature has today. We also looked at what it did yesterday and 2 days ago to somehow show an evolution. We didn't go further back because already the 10-day period in which we wanted to predict is pretty long. Looking back further, it didn't make sense.
And how did you? So basically, it's you're taking some autoregressive component into calculation.
Yes, we're somehow including those, but without calling it a time series. So that's why we had some adjustments to make because of the correlation between the consecutive days for an asset. And that's why we avoided including all of them. For example, for decision trees, we wanted to include one observation per asset, but that decreased a lot the data, and we didn't want to make that that change.
I understand. Yeah, so that's why you only take 3 days back.
Yes, yes, and that's why, for example, if we have a series of 15 consecutive days for a motor, we won't include them all in the model. We will choose one of them, and that one goes there. Because then, if not, those variables, so we will have a high correlations between the variables.
Makes sense, and yeah, then you won't be able to evaluate it correctly.
Yeah, theoretically, a random forest should handle this type of issue, but we found it better to avoid it altogether.
Makes sense. Have a question that let me rephrase this. So, how big is the training set in samples? Because in megabytes, yeah, who cares?
Well, in samples, meaning
The
how
rows.
many the rows, it's big. So we have approximately 3,000 assets. No, no, 2,000, because we only look at motors. Multiplied by 20, multiplied by the number of days in 2 and something years, 2 years and a month. So it's big.
Quite.
It's big, but it was trained once, and afterwards the model was saved, so we don't have to do the computations every time.
And how do you store it to get back to? Do you store it as I don't know, in a database,
Yes, we
CSV
have.
files?
No, we don't use CSV. That was my initial approach when I first started using Azure Machine Learning Studio, and I figured out it won't work. No, we have a database especially for that. It gets updated every day with new data. It's different from the operational database because, well, with the computations we do shouldn't interfere with the normal business. So
Right. So basically, you update the database daily, but you've only trained the model once, and then
once,
so how do
once
you know when to retrain? How do you
we
know
have
when the data is out of out of sync?
we have a daily job that goes through all these cycles. So it updates the data in the modeling database. Let's call it that. It calls for new data, so data that hasn't been predicted yet. So it hasn't been scored yet. and it sends the data to the Azure Machine Learning Studio. Azure Machine Learning Studio comes back with the prediction, and we store it via the backend in the operational database, where we also have the actual value of the alarm state. Well, if we look to, we have to wait 10 days in order to get the actual value, but that's how we compare it.
So you basically just compare the real observed accuracy of the model to the one you expect from the evaluation phase. But
yes.
you don't monitor the data distribution, or you don't check for data drift. That's what I'm.
Well, basically, we should be able to see the data drift if we see differences from one day to the other. We did that at the beginning. We continue on doing that, and that's why I said that it was important to choose a model that can be retrained easily, because we expect something will change, and the measurement types that we receive for the motors will change, and probably the behavior will change. So that's why.
Makes sense. Makes sense. Yeah, so, sorry, those were my my personal curiosities. But back to we have got quite a few questions. So next one being, did you train one model for each asset class, or a model for each separate motor?
No, so one model, so one random forest, for example, for motors, not for each separate motor. I guess that separate motor means motor with number 2000 and something, right? No, so we took all the motors together, and we trained a classifier for that. But we do treat separately the motors from the bearings for the pumps and so on, because even the measurement types are different. So even if we would like to, we couldn't treat them the same way.
So they're not easily, it's apples to oranges, basically.
Yeah, exactly.
I have to say, Dan, sorry for me monopolizing this this part. I know some holes are being drilled near the office.
Yeah, it's not a problem. That's why I kept myself on mute, because somebody's apparently redecorating at the floor above. But yeah, I can also chip in reading from the list. There's one question asking if this is by any chance publicly available.
No.
I guess not.
No.
That's what I thought. That's what I thought. But then we're happy that you're here and you're giving us the insights. And next one from Valentin. I'm also highlighting them on the screen. Do you assume that all motor data come from the same underlying distribution, or do you train a separate model for each one?
No, we didn't train a separate model for each of them, because we have a lot of motors. So it's somewhere around thousands of motors. And also we have to know what new motors will behave like. That means that every time a new motor, if we would assume a different underlying distribution for each of them, it would mean that with each new motor, we have to add a new model. And it's not... Of course, that would mean, a greater accuracy, and all those metrics would improve, but it's not really feasible.
Right, yeah, I can imagine. Next one, more about so is predictive maintenance still a thing, or instead of preventive maintenance versus predictive?
I'm not sure. So I guess it's still a valid option, but usually what I've seen, at least, is that predictive is the most widely used.
Yeah, and I know a couple of examples that in the automotive industry also it's used as well. Going further, how do you decide upon the threshold value?
The threshold value, I guess it refers to the threshold value for deciding on the labels. We found that it doesn't change as much as we would expect. So we decided on 0.5, and yes, it's the default option. But the things don't change as much if we play with that, because most of the motors that go into alarm state and it identifies have a great probability of going into that state.
Thank you. And
that's why defaults are important.
And we have a couple more. Alexandru is asking, yeah, I think this was a follow-up question from a previous one. For what time period was the prediction okay?
You mean the data drift controllable? We checked. I think that's what he's referring to, right?
Yeah, I think so too, but otherwise, Alexandru, give us a sign if we're off with this one. But yeah, go ahead, Victoria.
Yeah, so what we did was we checked for a couple of weeks, and the results were pretty much the same. So maybe differences of 1% or something like that in terms of recall and precision. There are still differences from one day to the other because that's how the data is and that's how the motors behave. But it wasn't a change, a significant change. So we didn't need to readjust the model just yet. So it's not in terms of hours, it's in terms of days or weeks.
All right, and I think we have, yeah, we have 2 more minutes and 2 more questions. Perfect. So one about model explainability. Have you looked at this or feature importance? And if so, what was the feature that influenced the prediction the most?
Well, yes, we looked at that. So for the motors that went into an alarm state repeatedly, the most important variables were the ones that we actually constructed. So looking at the history of alarms, so the percentage of alarm days in the last 30, the maximum consecutive days between 2 alarms, and so on. For the second model, for which we didn't have a history of alarm states, it was important the variable that looked at the alarm state today and in the previous days. So it's actually, it makes sense, but it's somehow, the results were in such a way that it confirmed our hypothesis.
Okay, and from Raluca, how did you control for class imbalance dataset?
So we did try to apply a method for balancing the data sets, so SMOTE. We found that the results are pretty much the same. And what we did was simply, when evaluating the model, we didn't take accuracy into account. We looked more at precision and at recall, because again, the adjustment didn't really do much for our data.
All right, so basically, yeah, just take the taking the good metrics into account.
Yes, yes.
Yeah, I think Alexandru came with an expansion of the question. So basically, preventive maintenance should be done in 1 week, for example. Maybe if the prediction is after 2 weeks, then 2 weeks are a window too big, and the prediction will not be accurate. But yeah, those are specifically for time series forecasting. Not sure if you're phrasing the problem like this.
Yeah, no, we're not. We're not. And Yeah, but I understand, because in time series, basically the prediction, the interval, it gets wider as time passes. Yeah, it wasn't the case.
Yeah, but good. I was thinking that that exact same thing, but then you said.
Yeah, that's why we avoided going in with the time series approach, because we would get into all sorts of issues, and the data with the gaps that we have, it wasn't feasible to do so.
Yeah. Fingers crossed someday.
Yeah.
Somehow. All right. Well, I think that's it, both from for the questions and from our I mean our time here. So thank you very much, Victoria.
Welcome.
Yeah, thank you. It was quite a Q&A session. So I think, yeah, it's been very fun watching it. At least, yeah, we're just helping show the questions on screen, and you did all the work, and everybody from the audience. So great stuff. And I think, yeah, we can take another short break around 6 minutes or so, and then we come back with the next session. Till then, have a great day, Victoria, and
Thank you.
see you soon, everyone.